Tomorrow is largely the systems, the water, sewage, and power, they're all interrelated. So that's why I talk about them all at the same time. Today is the basic structure, which is totally integrated with the heating and cooling, and in fact integrated with the systems as well. So I mean, a way to look at this is these are machines. They're not, they're shelters, they're homes, they're houses, whatever you want to call them in terms of that. But they're machines, and the look of them and the structure of them and everything about them is a result of what it takes to encounter the natural phenomena on the planet that are going to provide what you need. In other words, if you're going to catch water, obviously you're not going to do a roof like this. You're going to do a roof like this. And the same for the thermal, solar, electric, everything. So in that they're a machine, an easy way for me to explain it to myself is it's much like the human body. The human body is a circulatory system, a nervous system, a digestive system, a respiratory system. All of these systems are in the human body. You can't just apply these systems to the human body. The look of the human body is really a result of these systems. And these buildings are pretty much that way. So you can't say, well, I want my respiratory system on my leg or something like that. It's not going to work out. And it's almost that ridiculous. People tell us we really like this concept, but we want this here and that there. It's not that easy to do that. It's the machine and the understanding of the encounter with the natural phenomenon is what designs it. I don't really design this machine. I'm just finding it. I'm finding how it works. And I'm finding more. We've been doing this. I've been doing this for 40 years, I guess. And each year it keeps evolving more. We're just now scratching the surface of what is really possible in terms of encountering the natural phenomena. So the relationship of these buildings to the human body is a good way to look at it, because then it causes you to understand why you can't really have your particular design and then apply these things. So today we'll get into the structure, which involves the heating and cooling. And the component of heating and cooling is thermal mass. And a lot of people don't really, even architects and engineers really don't realize what thermal mass is. The way I look at it, and the book Comfort in Any Climate goes into it, but if you have a chunk of matter, two chunks of matter, one is mass and one is insulation, and there's a big difference. In mass, it's dense. The molecules are all really tightly packed. That's what creates density. And because they're tightly packed, temperature can just move through it, passing from one to the next to the next to the next. So it's very dense. Insulation is just the opposite. Insulation is a bunch of air spaces, really, created in a lot of different ways by weird materials or natural materials. But what happens with insulation is, unlike mass that'll just let temperature pass right through it, and if you trap it with insulation, then it gets stored in it. Insulation stops it. You can't, the temperature, whether it's cold or hot, it has a hard time traveling very far. So insulation really blocks the movement of temperature, and mass allows it to just go in like water going in a barrel, really. So if this is a dense chunk of mass, temperature can go right into it. And so these buildings, if you take a dense chunk of mass then and insulate three sides of it and subject one side of it to a temperature influx, be it cold or hot, it's just going to go in here. It can't go out because of the insulation, so you're trapping it. Very much like water being caught in a barrel. Temperature is caught in mass. So that's the building block of these buildings. And so the ideal wall then would have mass and insulation. That's the difference between this and straw bale. Straw bale construction is a great method of building because it's using a renewable product, but it's only insulation, so it doesn't store the temperature. And an example of storing the temperature is like if you take a cast iron skillet or and a tin pan, both, and put them on the stove at the same time. The heavy, dense cast iron skillet gets hot, the tin pan gets hot. You turn the stove off, and really less than a minute later, the tin pan is cooling down. 5-10 minutes later, the iron skillet will still burn your hand. That's the example right there of mass storing energy. And so that's the thing that we determined decades ago that you should build buildings out of. Now, you couple that with the fact that, so we're looking for a massive way to build. In the early days, they were using, water is a very dense mass, so they were using drums filled with water. We actually did some water can houses, adobe, stone, but we were at the same time responding to the garbage situation on the planet, and we were building buildings out of beer cans before we even stumbled into this mass thing. The mass thing kind of came out from the physicists in the early 70s when we had the first hint of an energy crisis. And people were all the engineers and scientists were trying to build mass into houses. We were already fooling around with building houses out of beer cans, so we looked around at what else there was a lot of on this planet, and it was tires. And we started stuffing dirt into tires and then beating it into tires. And so you have a tire that is a steel-belted rubber casing, and you beat it full of earth. You have a 2.5-foot thick chunk of mass encased in steel-belted rubber. The material that you're using is dirt, which is everywhere. Tires are really everywhere. Tires are indigenous to the entire planet. If you came here from another planet and saw all the tire piles and the tires, you'd think they grew here just like trees. And in fact, they do. I mean, we've been everywhere. Bolivia, India, everywhere we go, they've got tires, just like they have trees. So they actually have a problem with tires. You never hear anybody saying there are too many trees, but you do hear people saying there are too many tires, and too many people probably. But anyway, so tires are indigenous to the entire planet. They are a great, massive way to build. They're low tech. They don't require equipment. They require very little training. So when we were trying to evolve a method of building a mass building, we stumbled onto this really, and that was 30 years ago, and we really haven't found anything better. In other words, if I found some better way to achieve a massive structure, I would use it immediately, but I haven't. So and when you put all these criteria together, it's really almost unbeatable. The fact that they're indigenous to the entire planet, that it's low tech, that it's getting rid of something that we have a problem with, that it is structurally super. I don't know if Kirsten showed you the cement truck loaded driving onto the tire wall last night. It's super structure, and it's very good for earthquake because it's resilient, and it's, like I say, it's mass. It's mass that stores temperature. So that's what we started in the old days, building these U's, very much like that, and out of tires, and admitting the sun from the south. And we had, that's what this building really is. This building is I don't know, 12, 14 years old or something like that or more. It's out of date, really, but it's still, in terms of taking care of you, keeping you alive, it can produce food, some, it produces water, it produces power, and it stays pretty much this temperature year round. We open windows in the front and skylights in the back for cooling a little bit. We've refined that radically now. We obviously get the heat from the south, and this is a tire wall. The shelf is actually the mesa floor, so it's only tires from there up, and the earth shelf is just plastered earth cliff all the way around to there, and then that's a full-on tire wall. But this room is like a really good example of just like the early simple method of doing this, and we just buried it, put good insulation on it. I'll get into the roof slopes and all of that more with the water tomorrow, but you can see that this room is designed by the phenomena. We need the sun. The sun's from the south. The sun's not from the north or the east or the west. The major heating sun is from the south, so the building opens up to the south, and it's a pocket that stores temperature. And so that's the early rationale for how these were built, the material to build them out of. And it's like always, if when we look at the tire situation, we're killing a lot of birds with one stone. We're getting rid of a product that's a problem, and we're providing us a building material that is, like I say, indigenous to the entire planet, and it's low tech, and people can learn how to do it. And when it addresses that many issues, it starts to have extreme validity, let's say. So the component that we're doing these with is a mass component that has all these other attributes. Like I said, if I found something better, I would be using it in a heartbeat, but I haven't. So then we bury them, and this building's a good example of that. Well, then we ran into, this is just the structural thermal side of this. The power, water, and sewage side of it even gets more complicated in terms of what we ran into. We ran into, like in an extreme situation, a room like this could get down to 60 degrees. And I was fine with that. 60 degrees with no fuel whatsoever when it's like 20 below zero Fahrenheit outside. I'm like, that's a success story to me. I actually got sued because there's a regulation, let's call it, in the codes that says that 41 inches off the floor, a building has to stay 73 degrees day, night, winter, summer. That's a regulation. That's in the codes. And of course, all buildings are set up to do that. That's the way the engineers design the heating systems. And what they haven't faced there is that if the electricity goes off or the gas goes off, that 73 degrees goes away. But as long as the electricity is running and the gas is running, they can maintain that, and engineers design buildings that way. And so I found myself in a whole different realm here. Okay, I can't maintain 73 degrees. I can keep it between 60 and 80 with no fuel. And so I had to go to court, and I tried to explain that to the judge. I said, well, what if the power goes off, electricity goes off, or the gas goes off, that 73 degrees is going to drop drastically. That, in certain cases, like in Maine a few years ago, the ice was on the lines, broke the lines. People were without power, and their toilet bowls were freezing. They were gathering together in gymnasiums and armories and things like that with forced heaters, propane heaters, just to stay warm. Their houses were worthless, not usable. So I said, Your Honor, what if the power goes off and the gas goes off, that 73 degrees is not going to happen. Here, yeah, we have a lower temperature, 60 degrees is a low and 80 degrees is a high, but it's going to be there no matter what. Judge didn't buy it. So yeah, I got fined and everything. So what that caused us to do was, and that's the kind of, there's so many things like that that have happened. The judge in that case, this was, I don't know, 8 or 9 years ago maybe, but the judge just wasn't even willing to talk about the possibility of the power flailing or the gas not being available. So we were wrong, we were fined. So anyway, that caused us to take this very simple thing and make it more complex. And it did make it cost a little more, but in a way it was a good thing because now we can the corner cottage building, which will be on the tour, I don't know who's staying in it now, but and it is pretty much new off the line, not even totally finished in terms of landscaping, and it's obsolete. But and that's what happens. I mean, like it's evolving really fast, and because we just keep learning more. We're using the corner cottage design for the new education facility next door that the governor is paying for. That's an interesting situation right there because I went on and got in more and more trouble with these regulations, and they took my license in New Mexico 5 or 6 or 7 years ago, something like that. And then a year ago, the governor gave me $300,000 to build a building to illustrate this stuff. So it's like, what am I doing wrong here, or what am I doing right, whatever. I call it getting served shit and peanut butter on the same plate. But and it's always that way. Anyway, as a result of that, the corner cottage pretty much, if you there's a little teeny bit of education in how to run it, but if you run it right, and it's very little to know, corner cottage stays 73 degrees pretty much. I'd say maybe as low as 70, maybe as high as 75 or something like that. But anyway, it takes that range of temperature that used to be 60 to 80 and brings it real close to the law. And of course now a judge would say, a judge would agree with me now. They would say, if you can keep this building within 8 or so degrees of 73 without fuel, then that is a success story. But 10 or so years ago, they weren't buying that. And so what it did is launch us into taking this science, let's call it, a little further. So like the early sections then. So I mean, what I'm getting you to do then is understand why these designs are the way they are. And because people come here to either build these for a living, to build them for themselves, to share the information, whatever. And it's really important to know why we're not just doing these because they look cute or whatever. We're doing them because we keep finding more and more ways to fine-tune this encounter with natural phenomena. We're encountering the sun, and we're encountering the thermal mass that's in the earth. And the thermal mass concept. So what we have then is a section that we used to just have the tires, stacked up, and here we have a roof like this and like that. We've evolved out of that due to the, I'll talk more about that in the water situation. This is the angle in this building. This is the angle of the winter sun, to bring the winter sun in here. And even on corner cottage, I believe we still have this. We do this roof slope to let the sun melt snow before it evaporates. But we've evolved out of that. So this was our configuration 10 years ago. Well, the configuration now has evolved. We've gotten a way to melt the water with the sun. So now, see, this makes details and expense. So now the newer designs, which we call the global design, The newer design is a roof is is one configuration, one line. That's obviously cheaper. Has a greenhouse here, and this building, see, has a greenhouse, but it has also got a greenhouse here, glass. And so what that means, we're into this thing now we call internal space, because out here it could be minus 30 in this first greenhouse, which you'll see at Corner Cottage and the Phoenix and even in the global models now. It could get down to 45 or 50 in here. But this is for plants, not people, but people do hang out in there a lot of the time. Then the internal space, this becomes a buffer zone for between the outside space and the internal space. People hang out in here, and they are not subject, this buffer zone protects them. It's like and you rationalize it, or, it's square footage, you have to pay for it. But it grows plants, it treats sewage, creates more roof space to catch more water, and becomes a buffer zone between you and the outside. We even have some where we have gone to one more outside. So there's 2 buffer zones if in extreme situations. The Phoenix illustrates that a little. We play with all kinds of extremes here. This is a good place to develop these kind of buildings because we do get seriously cold here, sub-zero, if you're talking Fahrenheit, 30, 35 below. And we get up to 105, so we have to make the buildings cool and warm. But mass is what does that. So now we do one, so we have taken just this simple thing and made it a little more fine-tuned with all of this, quite a bit more actually. Of course, there's super insulation on the roof. And it turns out that these ventilation skylights are, in the winter, that's a cold draft coming down from there, no matter how tight you seal it. And so we're trying to buy every degree that we can. So we took them out and we put them in the greenhouse now. And you'll see this on, Kirsten will point this out on the tour, but look for it. Now we have tubes coming through the burial that this is called this has just been evolved in the last year or so and getting better. What happens is in this greenhouse, it gets intensely hot up here. And that heat wants to rise. And we have a skylight to let it rise, to let it escape. And the hotter it is, the faster it goes out of there. Well, when it leaves, you can't have a vacuum, so it's going to create a suction. And what it does then is it sucks air through these tubes. And these tubes are buried in the burial. So we have, it's almost, I think the physicists call it a convection engine, convection-driven air movement. No fans, nothing, but there is air moving. And we just did one up in Miles City, Montana. It was 105, it didn't have the double greenhouse, the third greenhouse had the double. It was 105 outside, 71 inside. And that would have made the law happy. And people would sit around this at lunch because they're coming in from working outside in 105 degrees and sit around these tubes and put their bottles of water in them and all kinds of stuff. You could see it was working. And this is with no fuel. So now we've taken this configuration that we got busted for a decade or so ago and taken it further, removed the heat loss of the skylight, created even better ventilation, and done one more thing. We do now what we call a thermal wrap, and you can see this. I think we've got one under construction called the Global across from Corner Cottage. Thermal wrap is we take rigid insulation and go out another 3 feet from the tires. And so now we have trapped more actual earth mass to work with the tires. The tires become the structure and mass, but we're adding another 3 feet to that mass by isolating it away from the cooler earth. Because see, that it's the cool earth that cools off this air. This air goes through the earth and it cools it off. Well, in the wintertime we plug these and the frigid air goes down into the earth 3 or 4 feet, but it can't get through this insulation. So now there's close to 6-7 feet of mass that belongs to this space. And the way that works is it's an actual, I do observe laws of physics. I don't really observe other laws. But laws of physics I call unarguable. And you can't argue with the sun. It's going to do what it's going to do. But anyway, a law of physics is that heat moves to the cooler place, not vice versa. So what happens is when warm air in the winter, say, is coming through these greenhouses, it heats up this airspace. Well, this mass space is cooler. So the heat leaks into it, and it just stores it because it's trapped by this insulation, this thermal wrap. So this warm air in this space leaks into the walls due to the law of physics. Well, what happens then is, and people that stay in, we have these nightly rentals that we use. That's kind of it was an accident because, see, the early days, I think Kirsten probably showed you some of the early buildings. It looked like they landed and whatever, and not marketable buildings. So I had a bunch of these unmarketable buildings. People wanted to look at them, stay in them, but they certainly didn't want to buy them. And if they did want to buy them, the banks wouldn't even consider it anyway. So here I am stuck with mortgage payments on a bunch of weird buildings. And so I started renting them at night to people, and that turned out to save me from going bankrupt, basically. And so now we do it, but we do it now to show people, to give people the experience of living in these, because a lot of people think that if you're going to be sustainable or green or whatever, you're in a teepee out in the desert, but they don't realize that you can have flat screen TV and high-speed internet and all kinds of goodies, normal life. So anyway, the people that stay in the nightly rentals would come to us and say, what the hell's going on? We go to bed, it's winter, we went to bed and put blankets on, and the sun went down and the airspace got cool, so we went to bed and put blankets on. It wasn't cold, but it was cool enough in the winter to have a blanket on. And at midnight or 1 o'clock, they wake up and kick the blankets off. And it said, it's like a heating system is coming on, or you got something you're not telling us, or whatever. And so what's going on is, and they've told us that in many ways. I mean, they've come and actually said, what is going on? It felt like a heating system was coming on at midnight. So what is in fact going on is the sun goes down, the airspace in this internal space, the warmth cools down, from heat loss through both glass spaces. It's slowed down by this, but it still cools off. And eventually, in the middle of the night, this space gets down to maybe 69 degrees or something. Well, the walls are all stored up at maybe 73, and it's just a few degrees different, but that's what it takes. Maybe this even gets the air temperature could even drop to 67 or whatever. It's still lower than the temperature in the walls, so because of physics, the air starts leaking out. It's just like turning a furnace on. The minute this airspace gets lower in temperature than the massive wall, and there's a tremendous amount of mass in a 7-foot thick wall all the way around your building, the heat starts leaking out, and it just heats up the space. And so that just keeps on going off and on, natural phenomena. We keep, so you can see from this building here how we had a handle on it in the very beginning decades ago, but how it's refined in many, many ways now. So we can keep the space in something like the corner cottage at like 73 degrees. And I would say between 70 and 75 is largely where it hangs. It may get up a little higher, a little lower, but it's close enough now, much closer than this building. And so that has become, see, this tube thing, we've been doing it in the tropics. We did it in India, in Hawaii, Nicaragua. We started doing it in the tropics. We weren't even doing it here. But we started doing it just to cool off in the summers here, and we started doing it here really to create ventilation without heat loss in the winter. And then we started seeing that totally cool air was just moving through the building. So this refinement is really in the last year and a half. The thermal mass has been around for 4 or 5 years, something like that. The thermal wrap. The thermal mass was there from the beginning. The buffer zones, they happened in the last 4 or 5 years. So when you apply all of these tricks, then you end up with a building that is just going to sit there without fuel and take care of you. And we have gone through many models. The Earthship designs, they have what we call the packaged, and the package with the double greenhouse then evolved, which is close to what I'm talking about now. The modular was the circles and the U's, and then the hybrid was a combination of both, and of course custom is custom. We can't, no matter how much money you have, we can make a custom building that's all beautiful and looks a lot more interesting, but we can't really make a building that works better than this one that we call the global model now. And now this one is what we use in the tropics because it stays cool, and it's what we use in the winter, in the extreme cold. We do take it a little further. If it's super extreme cold, why we add another greenhouse. And it's easy to justify this because, like I said, the second greenhouse is, and the third, is treating sewage, which I'll go into tomorrow. It's growing food and creating more roof space to catch more water, creating the convection engine to cause the ventilation, and becoming a buffer zone. It's like, it's like tires. It's like there's 6 reasons to do this, just like there's 6 reasons to use tires. It's not just one thing, and that justifies it. Because people are, when you're paying, these cost in this area $205 a square foot. That's about what a good economical but good conventional building costs here. Adobe's in Santa Fe cost $350 a square foot, and these are better. So it's in the price range with regular buildings in the developed world. And in many places it's allowed in the developed world. But it's one configuration now that we're using everywhere. We can, these buildings then obviously look in floor plan. I think they've got drawings here of the studio version, the 1-bedroom version, the 2-bedroom version. You'll be on the tour, you'll be able to see a 1-bedroom version of this. You'll be able to see a 3-bedroom version of this under construction. You'll be able to see the out-of-date version of this, which is Corner Cottage, which is really a package design with a double greenhouse. And see, we evolved the package design more than a decade ago just to simplify this, because what we found out was once we started building these kind of spaces was still, and it's still true today, the most prominent selling home in the United States is those manufactured houses that they bring in on a truck, set them up on concrete blocks, hook them up to all the utilities, and they start falling apart immediately. And they pump fuel into them and water and sewage out of them. But they are easily available to people. And we then, over a decade ago, started realizing that we have to make this available to people. It can't be more expensive. It can't be, it has to be something that's even more available to people, because money talks, really, and we're trying to evolve beyond that in a lot of ways. I'll get into that. But if you're playing with an idea that has to be purchased, then it's got to be the same price as the other things on the market. So that manufactured housing is what is the biggest seller. That's what people buy. So we came up with a package design that worked for that. And then it just had a vertical face. And the reason we call it the package design is because it was so simple that we could just, we could provide a kit almost that people could just put it together, and we could make components. So we were aiming at, you know, making this more user-friendly, because these buildings, these older ones, had a lot of strange details that required more skill. So we were trying to take it so that you could just assemble this building. And they worked pretty good. We did a lot of them. And then we added a double greenhouse to it. And then we got rid of the sloped roof because we decided we could heat the roof with solar rather than having to have it shaped to face the sun. And so the package then evolved into a double greenhouse package, and that evolved into what we call the global Earthship. And we've got a lot of these going around the world now. And we can do one of these, like we just came back from Miles City, where in Montana, where we put one up in 8 weeks, totally turnkey, everything working, 2-bedroom. And so we got the time down, we've got it to the point where this is a product now that we're ready to take out there. There are 6 points to these buildings, most of which, half of which at least, I'm going into tomorrow, but they are built where, everybody's looking at carbon zero these days. And so building with recycled materials is a huge thing. That's part of the rationale for using tires, but not the only rationale for sure. And the cans and the bottles. We were doing that before we were doing anything. And building buildings out of cans just because the media started screaming about garbage being thrown everywhere, and 30 years ago, 40 years ago, and it hasn't stopped. So that we were doing that then before the word recycling was even a word. So it does, in terms of a carbon zero building, if you're using a material like tires or bottles or cans that is taking the place of a manufactured material, and that manufactured material takes energy to manufacture it, you're starting off with a material that doesn't have to be manufactured. There's a double thing there. It also takes energy to do something with the cans and tires and bottles. So you are getting rid of that energy because you're using them rather than using the energy to get rid of them. I was in Norway recently, and they have a giant recycling company, but it's just like the energy that is used to recycle all these materials is unbelievable, really. And then they ship them somewhere. So shipping, you're taking the place of shipping because you're using a product that's laying around. You're taking the place of manufacturing because you're using a product that's already manufactured. And you're taking the place of disposing of garbage because you're using garbage. So there's 3 ways that these buildings start off with actually a negative carbon footprint when you're going out there and pounding dirt into tires. So it starts off with a negative carbon footprint because of building with recycled materials. Then thermal solar, which is what I've just been talking about, heating and cooling, and these are the major points of these buildings: thermal solar, heating and cooling, building with recycled materials, and then and so the design of the buildings is a result of what it takes to use recycled materials and what it takes to achieve thermal solar heating and cooling, and you can see how it's evolved. And then solar and wind energy, of course, which we'll go into tomorrow. Water from the sky, harvesting water. And then contained on-site sewage treatment. Contained sewage treatment. And so this is getting you off of the grids, and sewage treatment is getting to be a big deal because it's all going. They kind of halfway treat it in sewage treatment plants, which again takes a lot of energy, and no pun intended there. So it takes a lot of energy to treat sewage, And sewage is a valuable thing. Sewage to me is gold. It's compost. It's providing energy for food, which is the 6th point, food production. So if we can make a building that addresses all of these issues, who needs the government? Only to hinder us from doing it. Yeah.
Doesn't it also regreen because the black water plants grow that wouldn't normally grow in a...
Yeah, and you'll see, I don't know if Kirsten had in the slideshow, but if you get to see some of the older Earthships, I have a great picture in one of my shows that shows one of the buildings here, and you've got the barren, deserty mesa, and it might even be in one of these posters, but his Blackwater system, which I'll go into tomorrow how they work, has just gone off. It's like a big oasis of green with birds and owls and creatures living there, and then you see the periphery, all the barren mesa desert. And so yeah, these buildings actually cause green to happen. So, and that's because they don't throw their sewage away. That's because the sewage is gold. The sewage can give you a green surrounding. So the regreening of it is definitely an issue. But if you're dealing with, just think of this in terms of the issues in the cities and other countries. How much of a garbage problem there is. New York City's taking it out in barges and dumping it in the ocean. It's being, everywhere I go, the first thing they do is they take me to the dump, and there's mountains of tires and bottles and piles of refrigerators and ranges and things like that. And we've got ways to use all of that. I imagine Kirsten showed you how we use the washing machine refrigerator panels. That's new in the last 4 or so years. I was in Hawaii, and talking to a grade school kids, and they took me to the dump, of course. And it was the little island Molokai, and they took me to the dump, and there's where I first got this idea. I've seen this before, but there was a big mountain of refrigerators, ranges, washing machines, appliances that went bad. And we had been switching, and I'll go into this tomorrow, our roof material to metal because metal catches cleaner water. And this mountain of washing machines, they're all full of these baked on enamel yellow and green panels of metal and nice colors and everything. So after I came home from that trip, we went to our dump, and there was sure enough a mountain of refrigerators and ranges. So the crew went out there. We took a solar array and a solar trailer so we could plug in these electric snippers. And like if this is a panel on a washing machine, you just stab the corner of it, make a hole, take the electric snippers and snip them in there, and you got a panel. So we just go to the dump and harvest metal. You'll see it when you go to Corner Cottage has got some of it, across the street the New Global has some of it, and the Phoenix has got the best application of it. It's like artwork there. As a matter of fact, I just got a new 1970-something Mercedes that was all beat up, and we patched up the body with washing machine parts. It's beautiful.
It looks like paint swatches, that you find at the paint store.
Yeah, it's great. And then we found a couple of pink ones here and there, and we really like the pink, so we paint some of the panels pink with metal paint. But anyway, we're harvesting metal now out of the dump for roofing. And so every city and country has serious issues with garbage, and in terms of what to do with it. And then when they do something like Norway does with it, to me that was scary. I mean, they had a factory of machines chewing up energy and trucks hauling it off to other parts of the world and whatever. to me, that was insane. I mean, they thought it was a great thing that they had such a giant recycling situation, but I was just seeing energy used like crazy to recycle. All we're doing is gathering stuff from the dump, bottles, cans, tires, cardboard, washing machine parts, and we'll continue to find other goodies. So building with recycled materials is not just like it's a logical thing. There's really good materials, and in fact, I can't find, manufactured or not, a better material than tires to build with. If somebody gave me $30 million and said, develop the best develop the best building material you can find, I'd probably invent a tire. So it's like a super relevant issue that, aside from housing or anything, every city is dealing with. Well, then, of course, the energy consumed to heat and cool homes. Everybody probably knows that the CO2, I think they argue, but between 30 and 50% of the CO2 impact is from buildings. And that's obviously largely from heating and cooling buildings. And so if you're heating and cooling buildings with thermal solar and trying to come up with little tricks to extend that, which we're doing, then you're affecting that issue that every country and city is facing. Solar and wind for the electricity, which again is affecting, if you're replacing a coal-fired power plant or a nuclear power plant or whatever, then you're certainly affecting, like when we were in Normandy, France doing one of these, they were getting ready to do two things in the neighboring area. And they were actually putting up signs and people marching and raising hell about it. One is they were going to do a new landfill for garbage, and here we are building a building out of garbage. And two is they were getting ready they were condemning a bunch of farms in Normandy, France, to run the big power lines down to the south of France from a nuclear power plant. And we were building a building that didn't need power. And so it caused a lot of commotion. There were 2,000 people there at the building the last day that we worked, and it caused a lot of commotion, really. They also took our crew in paddy wagons down to the police station too. I ended up having to go to court there. Pretty much everywhere we get in trouble. But then harvesting water. Water is, they say, a lot of people say the next world wars will be fought over water. If you get 7 inches or more of water precipitation annually, these systems work. I go into that more thoroughly tomorrow. Contained sewage, obviously, that's a serious issue everywhere. It's either going up in Colorado. There are so many developments all around Colorado Springs and Pueblo and Denver and everything that, housing built on 1/2 and 3/4 acre lots. Some of them have septic tanks, and some of the people have told me they walk out their back door and the ground goes squish under their feet because there's just so much. A serious example is a development in California, somewhere, I forget where it is, Southern California. It's an existing development, and they're getting fined millions of dollars a year because it's several thousand homes that's near the ocean. And so the homes are all sucking water out of the aquifer, which is creating a vacuum that's sucking in salt water and contaminating the aquifer of their wells with salt water. And then on top of that, they're putting sewage down it anyway. And so they're without water and sewage and getting fined until they fix it. And they were going to get our systems set up there. They're still going through the bureaucracy to try and do it. And that's the big issue these days, is getting permission for these things. And then the next thing that is starting to be an issue is food. We're producing, this is token here in this building. This is an old building. But the Phoenix, you'll get to see it on the tour, and some of the other buildings are more, but the Phoenix is really our effort to illustrate what you can produce in terms of food due to your treatment of sewage, due to your buffer zone. we're starting to produce food. And the Phoenix has got, we're taking it to what used to be called extremes, well now it's just the logical next step in my mind. The food production at the Phoenix is, I think 3 or 4 days ago, we went over there and dropped a line in the tilapia pool, caught a fish, cleaned it, skinned it, fried it, gathered some lettuce and tomatoes and peppers and other goodies from growing in the Phoenix and had a great meal. So we can, and we got lots of tilapia there now. So we are now getting to the point where our objective with the Phoenix is that a family of 4 could stay alive without anything. So when you put all of this together, we're talking about these are 6 food and sewage and water and energy and garbage are issues that every city in the world is facing, and I'm not saying we're the solution. What we're saying is we're addressing each one of these issues sort of in one blow called housing, you know, and it's working. We've been playing with it now for decades and keep evolving it and so on, and it's like a dichotomy or something, because we're seeing that this works, and we're seeing that we can make it affordable and we can teach people how to do it. And you know, what you should do coming to these seminars and being interns and whatever is I'm trying to illustrate the core thinking of this so that you know why these things are they're not really some architect's designs. We're finding treasure almost here, and that's kind of what it is. We keep getting more and more tricks, but another trick we're dealing with on the thermal solar heating and cooling, for instance, like in Norway, I've done some work up in Norway, and this building that is our prototype building now, even in Norway, would be the building that we would use, but we would probably have another greenhouse. But there's times in Norway when it's like, you know, the sun doesn't shine for 7 or 8 days, it's dark, it's cloudy, it's gray. Even though this building is tight and has its thermal wrap and its buffer zones, it's still going to get slightly cooler than you want to be. And but the things are so tight and so well insulated and have so much mass that it just like this is not one of the latest buildings, but the body heat of half this many people would heat one of these rooms. And so as a matter of fact, one of the projects I did when I was teaching an architectural course in Norway, and we built a tight little room about 1/4 the size of this room to illustrate that when you build a room with mass and super insulation and tightness, that all of a sudden you don't need massive forms of heat, you need subtle forms of heat that you wouldn't even consider. Subtle forms of heat are the heat of the human body, the 98 degrees of the human body, a laptop. You know, this room we built could be heated from 2 laptops from people working in it. And the way I illustrated it was we had these big thermometer on the wall, and there was a lot of skepticism. They almost made us quit, actually, because it was too unconventional for their European minds, I guess. But anyway, we got it built, and we took the last day we took about a dozen people in the room. They were faculty and funders of the architectural school, and we closed the door, and I told them to watch the thermometer, and it went up a degree, and you know they were, oh wow, and it went up another degree, and by the end it had gone up I think 10 degrees, and they were all these faculty, conservative funders of the school were screaming and laughing and yelling as they watched the thermometer raise just from the body heat of people. So it like brings the whole different realm of resources. You know, we're used to going out and seeking major heat from a coal-fired power plant or a nuclear power plant or a furnace or whatever. When you build the room with a lot of physics built into it, subtle forms of heat become available to you, like a laptop, like the body heat of people. And one of the ones we're playing with now that I really like is we're calling it a heat bulb. It's sort of this, I think it's going to be about the size of a stove and made of metal, and you put compost in it, and everybody knows that compost goes off, and what we're trying to find out, I've already played with it enough to know that it's going to work. I just need to get the logistics. So the ideal with this thing is that in Norway, where you've got 7 or 8 or 10 days of no sun, and you're starting to get cooler in your room, you just need, because the room is built right, you just need such a subtle amount of heat. And this compost bin, or heat bulb I call it, would go off. You'd load it up with compost in the spring, and this is what we're trying to find out is the time frame here. And then in the autumn, when you're going to start needing it, it's going off. It's hot inside, and it's just emanating maybe 100 degrees, 120 degrees of temperature. But that teeny little bit of temperature is even more than the human body engine. And it's just radiating this little subtle bit of heat out there. And that's enough to take the edge off of a cool room in Norway, if the cool room is built to contain everything anyway. And so, it may be that we'll find out you have to do it twice a year or whatever. But we're working on it right now. And I have, and for the last year, I've had a garbage can sitting in my office full of compost and reading out the thermometer as it was going up and everything. The guys that I had helping me, I sent them to Walmart to get me a garbage can. And I told them what I was going to use it for, but they just didn't snap to it. And they came back with a plastic garbage can, which would have just melted. But this heat bulb thing is just another trick which is involving biology and physics, to buy more heat without actual fuel. And so this is how we're taking this to areas where it's even, where it's ridiculously less sun. But every city and country is facing all these issues, and we have taken each one of them, and if you consider these like systems of the human body, we've interwoven them, and they're all interrelated to come up with this building now that we call the global Earthship. And we have a couple of examples of it here, and then everything else is a prototype leading up to it. The Phoenix is the best example of all of this put together in more of a flamboyant way to make it, it's not like what I would call an affordable application of all this, but it certainly is showing it in the most intense way that we can. And so what I'm getting at is, through the last few decades, we have evolved each one of these things seriously. And the problem now is being able to do it. I don't know where, everybody's usually in these seminars is from all over the country and world. What we're finding out is it takes a certain amount of effort to get a permit for all of this. We've got tricks to deal with it. Most of the time we've developed, we used to fight them, then fight them on a small scale. I've tried to join them. I've tried writing new laws. I've tried everything. And all of that takes time. There are some places, lots of them, that you don't have much trouble, and it's getting better because there's more publicity about, climate change and global warming and everything. So all authorities are getting a little better, but still they have to follow the rules and regulations, and the rules and regulations don't allow a lot of the things we're doing. But we're making a map of the U.S. and really the world. There are places where it just takes a little while longer, but there are places where it takes too long. And a good example is in Scotland in the last few years, I think it was like almost 3 years ago, they had a lottery in Glasgow. And their lottery over there is somehow split between the person that won it and the community at large. And so the community at large then gets to vote or agree on what they want to do with the lottery money. It was a few $100,000. And they chose to do a demonstration Earthship in Glasgow with their lottery money. This is the public. This is the people choosing to do this. Because Earthships are getting well known in Europe and the websites out there and whatever. And so the people made the choice to take their lottery money and build a carbon zero demonstration pavilion. And it took them 2.5 years to get a permit. Like that's insane. That's what, so that to me, now that, this part is the fun part. We're getting it better all the time. It works good now. It's ready to roll. And where we're at now is getting it so that people can do it. 2.5 years for a permit. It took us 3 years to get one in Brighton, England. I had a guy work for 18 months. He came to me. He had an oxygen tank on his back. I thought he was going to die in the next week. And he worked for 18 months to get a permit in Arizona, Pima County, Arizona, to get his Earthship built, and it's going up now. It's on the web. So it's like in a lot of developed countries and cities, it is difficult still. The further you get out in the boonies, the easier it is. And so what we find ourselves is, we try to support people and work with them and help them through the permit process and everything. And but as the planet situation continues to worsen, so to speak, we're seeing that these places that allow you to do, like third world countries are the Indian reservations. Like we did one up in Lakota Sioux land, and they just took us out there on Chief Crazy Horse's ancestors, descendants' land, and said, "Do it here." That was the permit. And so they have land now. They have a lot of money from gambling, and they got no rules. They could take the lead. Third world countries can take the lead because they aren't encumbered by all these rules and regulations. And in this country, we're taking a map, of the U.S., whatever it's shaped like, and we're going to map it online because there's these places we call pockets of freedom, like Montana. It's actually, this is supposed to be a free country. Well, let me tell you about it. But there are places like that. We've just noticed this recently, but people have, we've got people, we're selling drawings all over the world and then hacking through the permit process with them and sending off engineer reports and tests and studies and all kinds of stuff. So, it slows down the process of getting carbon zero building out there. And it's not, I can't really find whose fault it is. It's just the human condition has woven a set of rules around itself in the developed world to the point where they can't evolve without taking a tremendous amount of effort and time, and we don't have that. So it's an extreme contrast to have somebody walk in our office and a month later we're building a building for them in Montana. And that's happening. It happened twice in Montana, now it's happening in Texas. So what we're going to do is map the counties in every state, because this county that we did this building in Miles City, you don't need any permits.
In Montana, is the governor Schweitzer? Does he know what you guys are doing? Because he's
I'm not sure. We're as a result of our build there, they're wanting us to tell them about our gray water system and things like that. But I imagine it everywhere we go. It gets in the paper, so I imagine they're aware of it. We're not sure of whether we're going to do harm or good by pointing this out, but you take Montana and Idaho and the Dakotas and you start coloring in all these counties where you don't need permits. And now in Texas, we're in East Texas, no permit needed. In other words, the guy came in on East Texas. He came in to stayed in Corner Cottage a few weeks ago. We're going down there in 3 weeks to throw up a building for him. No permit needed. So what I'm saying is green carbon zero housing can, boom, exist instantly in lots of places around the U.S. And then, this is almost like the maps they make of the Democrats and the Republicans. You got the map of where you're free to take care of yourself and where you're not free. And it could be that a lot of people end up moving because it's beautiful land. See, there's some of the most beautiful land in the country is what they say worthless because it has no utilities. And it's also worthless because it's, doesn't have any rules and regulations. So there's a lot of that in this country. There's a whole lot of it in the rest of the world. Europe is one of the worst for not having it, but there are pockets in Europe too. So there are places where what we're saying now is, yes, we're still working on the codes and regulations and trying to go through the regular path, which is more time consuming and so on. But at the same time, we are going for these pockets of freedom. We have sort of got one here because of 2 decades of fighting.
I'm just curious, has your fight gotten any easier now that you've found these pockets where you've built them and proven that it can be successful? Are there other areas that have been fighting you that are becoming a little easier to get this done?
Well, there's no question that with the media, now there, it used to be global warming was kind of a freaky thing you didn't talk about, and now it's everywhere. Every time you turn on the television, there's something about climate change and everything. So it is getting easier. People are at least listening and looking at it, but they always come back to the same thing. It's a government employee, has a rule book. He'll lose his job if you don't enforce the rule book. I mean, I've even had him apologize to me for having to enforce it. But it's like, so what I don't know how many people have seen the movie. We introduced this law and fought through it for 4 years. And so I illustrated to myself, yeah, you can make new law and change things, but we don't have 4 years. We need to do this every week, every month. And so we have now evolved the law into what we're calling, what is known. It's an executive order. An executive order is a tool that any governor or president has to, and we wrote one for the governor of Arizona and for the governor of New Mexico, who's now on board with us, so to speak. We wrote an executive order that basically the bottom line with it is it's the way they did the atomic bomb. After Pearl Harbor, everybody was scared enough that within weeks they were out here in Los Alamos building a city, building and testing a bomb, blowing apart 10,000 acres. They broke the rules because they were scared. We're waiting for them to get scared enough, but the executive order is what allows a government to do that. And so we're writing an executive order that mandates carbon zero permitting. If you're going to build a home that you're claiming is carbon zero, and your proof of that is that you're not hooking up to any utilities. If you're going to build a carbon zero home, then you get a red carpeted permit in days. In other words, it red carpets carbon zero permitting. Right now, if you're a developer and you're going to build a set of condos, if you're going to build the typical junk condos that hook up to all the grids, you're going to get moved through pretty quick. If you can do some expensive water system and sewage treatment plant and whatever, all of which are half-assed. But if you're going to do a green condo, carbon zero condo development, there's going to be definitely so much new or unheard of technology that you're going to be on the permit level for 2 or 3 years.
Because you're not driving chemicals.
Yeah, because so there is the issue right there. It's very easy still to do the wrong thing. It's too hard to do the right thing. We're trying to get an executive order to make it easier to do the right thing, or the logical thing, as I would say, in terms of trying to move people toward carbon zero development rather than more of the same. And so that's the technology. This is what I'm going after everywhere. The governor of the Galapagos Islands has asked us to go down there. I'm going there in 3 weeks or 2 weeks or something. They have made a claim to the world that they're going to be carbon zero by 2015, and then he turned around and observed the fact that he didn't know how to go about it. So he goes online and finds these idiots out in New Mexico, yeah.
Have you looked into carbon credits at all as an incentive for this?
Well, I haven't, but my son has. Carbon credits is going to be a form of currency sort of in the future. What they're saying, I don't quite understand it, but they're saying that a company that's doing a bunch of bad stuff could donate money to us and get carbon credits. I'll take it, you know.
We're gonna do that stuff anyways.
Yeah, so in a way that's weird, but it's like, I don't know. But anyway, carbon credits is starting to be, you know, we're starting, I would say, if you know how to do the formulas and the application of carbon credits to an Earthship, my guess is it's going to come out with a negative carbon footprint.
So I sit on my Community Health Improvement Council in Farmington.
Yeah.
As a nurse, and one of our priorities for a long time has been affordable housing. So when we had our last meeting, somebody gave a big talk about the affordable housing, you know, going from homeless to actually being a homeowner and kind of all the things that we have in our community along that way. They were talking about getting people to be able to afford their first house. So I pipe up and I mentioned, you know, are we building houses that are worth buying? You know, and I said, you know, we can build off the grid, no utilities. I mean, you know, if it's possible. I was just wondering if you've had any experience working with like Habitat for Humanity or any of these groups that are that are out there building houses right now, you know, not for people that are upper middle class who can afford, you know, Pottery Barn and Earthships, but, you know.
Well, we've been approached by Habitat for Humanity several times, but it's never, they're building, you know, they have kind of a good thing of building houses, but the house, I've heard that through talking to them and having meetings with them, that a lot of the buildings that they build go up, but then they have, you know, just the same utility bill as anybody else, and they can't, when they get a home for an impoverished family, they can't afford to operate it. You know, they can't, and with rising, I mean, gas here, propane has quadrupled in the last few years. So when you have to heat and cool a building and provide electricity for it and pay a water bill and pay a sewage bill, even though it's given, the home is given to you, you can't afford to use it. So we haven't, nothing's materialized with them. We're still kind of on the periphery of reality, I think, in many counts, and maybe we'll end up staying there because I think reality is going to crumble anyway. So, no, we haven't gotten involved with any groups like that, although there has been talk. But so the issue then is for where to go from here is, yeah, at this seminar today and tomorrow and this afternoon, you're going to pick up the crux of how to understand these things and a little bit on how to build them. But there is a whole other issue, and we can, depending on where people are located, if you haven't gotten land yet, see, what I would say is a lot of people are that come to these seminars are looking for the place to do it. And so what I would say is, you would be miles ahead if you haven't got your land yet, to check around for the areas in your state or the area where you want to live, and see if you can find a pocket of freedom to do this, as opposed to a place where you're going to have to fight for a year or bastardize the design or whatever. They'll ultimately, you know, they will come around. And I can say that from experience because, you know, 8 years ago they were practically putting me in jail, stripping me of my license and everything else. And now the governor has given us $300,000 to do this building next door to demonstrate this. They're talking about giving us another $400,000 to add an addition on it where people can stay in it. It's called the C project, Sustainable Energy Experience. And now the town of Taos, on the other side, the state has given them the town of Taos land, and they want to do a visitor center, and they came to us and asked us to do the visitor center. So they have come around. I mean, we could easily screw it up and be right back where we started. But you had a question?
What other areas would you say are pockets of freedom?
Well, we have just kind of come across this concept or this observation. For sure, lots of Montana, but not exactly near Billings or Bozeman or anything like that, but not that far out. Lots of Montana, Dakotas, Idaho, even Washington State, Canada, then some of the backwoods states, East Texas, Louisiana, Arkansas, even Kentucky. I mean, every state, just go as far away from what we got is people on the staff now, we're starting this, taking every state, county by county, calling the county seat and asking, what do you require for a permit? Because it blew our minds to have somebody walk in here and a month later we're building a house for them. I mean, it just, the house is already designed. We tailored the design to their climate. And if they have the funding, then they, it's amazing to see that green, carbon zero building can happen like that. And it really emphasizes all these fights that we've been through over the last few decades, that the technology is here. I say it over and over again. The technology is here and getting better all the time. The thing standing in the way is the approvals to allow you to do it, and it's insane, but it's really, whose fault is it? I don't know. All the codes and regulations came about from, the big phrase they like to use is the health, safety, and welfare of the people. And so they're making them real safe for the next week, but in the next year, they're gonna all die anyway, so, yeah.
Dolores County, Colorado, you have an Earthship in Rico, which is up near Telluride.
Yeah.
And we just started some projects up there. There's no building permits required, there's just a septic and a driveway permit.
Yeah, and so that's fantastic. And septic is no problem, because I'll go into I may even get into it a little bit today. I'll go into the septic sewage system. We have inherently in the building a conventional septic system. That's one of the ways we have learned to do it is like I say, I've gone through all of the different levels of how to do this, from fighting to whatever. Fighting takes too much energy. I just tell them what they want to hear now. And you want this? You got it. I mean, it's like, and half of the officials even know that that's what I'm doing. But it makes them safe because they know that what's in their rule book is wrong. I mean, I've had health officials in Colorado ask me for a job. So we have inherently a conventional septic system. The way we use it as part of our unconventional system. The way I see it in my head is like when you got a dog and it's got worms and you got a worm pill you have to give it, you put the worm pill in a ball of hamburger and the dog just woofs it down. So that's the way I deal with the regulation people, I put it in a ball of hamburger and they woof it down. And it works. But still, there's still the process and everything. So it's like we're aiming for projects that, I mean, I'm not trying to be a doomsday person or anything, but, for us to spend our time fighting the bureaucrats as opposed to spending our time building an Earthship, it's way more important for us to build an Earthship out in the boonies, because the web, we were out in the boonies in Miles City, Montana, but Jonah, my son, puts it on the web. People see it going up. They see a carbon zero building going up quick, and the world sees it. And of course, that causes, I think while we were in Miles City is when the governor of the Galapagos asked us to come down there. And, or maybe I don't know, maybe it was while I was in Australia. It was just in Australia, the same thing's going on there. They need it desperately. They need all of these things desperately. But they're just, they get it to the certain point of recognizing they need it, and then they're hitting their brick wall of their own codes and regulations and rules. And so we're looking at trying to find pockets of freedom there. And the other thing with Australia is just like it is in this country. The place that's going to get to do it quickest is the Aborigines, and in New Zealand the Maoris. They say that this is the closest thing the white man has done to the way they believe, and so.
And it has a flat screen TV.
Yeah, yeah, and so we're now aiming our efforts at the quickest place we can do it. And not giving up on the other situations. Like I've had one, see, you can take all of these principles and they're new buildings. And we could build with an army of people, and we're getting an army of people basically. We could put an army of people together building these buildings all over the world, and we wouldn't scratch the surface of what the number of existing buildings are. So taking these principles and applying them in what is called retrofit to existing buildings is a serious issue. And it's not near as fun as going out in the boonies and starting from scratch and throwing up a carbon zero building. It's a lot more mental application to try to take an existing building and retrofit it. It's expensive as well. But we're doing it and attempting it. But what I'm getting at is we've got a project that's been on the books, on the drawing board and everything in Long Beach, California. Just a little $500,000 home that somebody bought and wants to add on to it and make it, retrofit it to be more toward carbon zero. They can't get it absolutely carbon zero. And they're coming up against things like it is in a historic zone. And we can't even put thermal windows in it, because you have to replace the windows with like kind of stuff, which is the old window weights and the old glass. I mean, it's like ridiculous. I mean, history is for history books, otherwise people are going to be history. And so it's like insane what's going on with retrofit. But retrofit is something like, it's something to have in your minds, because everybody can't build a new house. Some people are going to need to retrofit their existing house. And it's taking everything, all the principles are simply the same. It's the procedure and of applying them to an existing building. I was asked to go to Norway to teach a course, but at the same time, the School of Architecture in Norway, it's the Bergen School of Architecture, and they are not part of a university. They're just an architectural school. And they bought a 9-story concrete bunker grain silo that still smells of rotting corn and stuff. But the architecture students are in that building. It is, it's weatherproof, where it rains on it and it doesn't leak very much. But it's just concrete, 1-foot thick walls. And when I got there, it was in the winter, and the students are all in jumpsuits and hats and earmuffs and gloves, sitting at their drafting tables, doing architecture, freezing. And I pulled out my wool hat and gloves and everything just to be able to talk to them. And so they wanted me to help them figure out how to retrofit this building. And this really becomes a good approach to retrofit of cities. We had several discussions with all kinds of professors and designers and students and everything, and it was going to be super expensive to apply all of these principles to this building. But it was a 9-story building, and it did have a huge volume of space. And the concept, and that's the issue, is coming up with a concept first. The concept that we ended up with to retrofit this building was, it's such a massive thing that we determined that it was not a building. We called it terrain, just like cliffs and rock formations and whatever. So we called it terrain, and we quit trying to retrofit the building. We just went in and made little areas, like swallows build little mud nests on the overhangs of Super 8 motels and stuff like that. We would go in and apply all these principles to a little area. This little area is warm, has a little solar panel, has a little water catchment, has plants growing, and we just go in like a little cells of cancer almost and overtake this building. And rather than trying to retrofit the whole building, we took our space and applied all these principles to it. And so anyway, that's just another approach on retrofit, because we're trying the more or less conventional approach to this house in Long Beach, and it's like, it's been going on for almost a year, still don't have a permit. It's a shame, you know, that's the way it is. But so retrofit is going to be facing the same thing that that new buildings are. You're inhibited by the nature of the situation. Yeah.
Quick question, the last time we saw on the slides of the toxicity of the tires, how does your, whatever you put over the tires, prevent the toxicity from coming into it?
Well, there's two answers to that question. There's another question that probably would come up, and I'll go ahead and bring it out, is burning of the tires too. But the tire, when you go to a tire store, and it's got the show window and the sun coming through the window, you walk in and you smell the rubber. You know, it's off-gassing, they call it. So a lot of people ask that question. And we've gotten a lot of bad press on the website and stuff about, you know, this is garbage. We went through a period of time where we had to determine every building as a waste dump. So get a permit for dumping waste. So just paperwork. But so a physicist from University of Wisconsin, on his own volition, did a big, thick study on running air through tires, old tires, new tires, water, and so on. And he ended up with the thought that, I think his last paragraph said that living in a tire building is about as dangerous as eating a peanut butter and jelly sandwich. And so then I would get people that said, well, if that peanut butter and jelly sandwich is on white bread, then it's dangerous. But so you get your sticklers for sure. But the bottom line is, he proved that what he came up with was that tires, after they got 20,000 miles on them, have done their off-gassing, and they're not off-gassing anymore. But then two, they are buried. When you take a tire wall, and we pack out this, you'll probably be seeing or doing some of this today. You pack out with cans and mud and cement, and then you build that out to where it's tangent with the rest of the tire, and then you plaster that. So your minimum is about 1.5 inches to 2 inches of plaster over one place, but that grows to 3, 4, 5, 8, 10. So you basically are burying the tire. That's a tire wall. It's buried. Even if it was off-gassing, it's sealed. But they don't off-gas after they're old, and they're buried. So that is a non-issue, but we still get people worried about that. I mean, we have in the back of the Phoenix, when you go there, the tires are exposed. I mean, I don't think you'll smell anything back there. Then the other question that comes up a lot on tires is burning. Everybody's heard about the tire piles around the world spontaneously combusting, which they do. But that's because, if you take a crumpled up piece of newspaper with air all around it and everything, and you torch it with a cigarette lighter, it just goes up in flames. That's the way a tire pile is, with all the tires with air all around them. They can spontaneously combust, and it's hard to put them out. But if you take paper, which is very combustible, in a New York City phone book and put a cigarette lighter to it, it doesn't go off. It doesn't happen. That's the way a tire pounded with earth is. And that was my line, at least, that when people asked that question, that's what I told them. Well, that came true because an Earthship up here in the mountains went through one of the major forest fires we've had in the last few years. And I've got pictures of it. The front face wood burnt off, the glass disintegrated, the roof disintegrated, everything went away except the tire walls. They were plastered, and a couple of places, it wasn't a finished building. A couple of places the tires weren't plastered over, and that part, the rubber melted down to the steel belted stuff. But wherever there was plaster on the tires, the tire wall, they're actually going to build the building back on the same tire walls. So they don't burn.
One of your books as well, right?
Yeah, I think so. They don't burn and as used as a wall, and they don't off-gas, and they are indigenous to the entire planet, and you can make super walls out of them. And so that's the general look at the basics. I think we could take a 10-minute break and let everybody walk around, and we'll get back into some system stuff. All right. Well, I'm going to take a few questions, and people have been asking me questions, so I'm asking them to ask them again in front of everybody so that everybody gets the answer. But we're talking here briefly about the permitting in New Mexico, for instance. In New Mexico is where we developed this, so in New Mexico you pretty much can get a permit as quick as any other building. In Colorado, some counties don't even require a permit. Some counties are harder, and some are like New Mexico. I have an architect's license still in Colorado. They haven't taken it yet, so that helps sometimes. But we had people. This is again many stories like this. We had people that were in one county in Colorado where the plan checker was new. She was engineer educated, and she just made it really difficult for these people. And they had been working for 2.5 years to get a permit, and finally they couldn't wait any longer. And they went ahead and got a permit they just decided to buy a manufactured home that they bring in and set on concrete blocks, and that they could live in while they continued to fight for their permit for the Earthship. And they did it, and they went in. The only stumbling block on their permit for the manufactured home was they had to sign an affidavit that said they would not let any infants or elderly people go in the building for 6 months because of the off-gassing of all the weird materials in it. But they got the permit. They got the permit in a couple of weeks, where they'd been working on trying to get a permit for a carbon zero home for 2.5 years. They ended up finally getting the permit, building the building, and getting a divorce. So, somebody, you had a question.
Your company, do they do the package plans like Shell and Power for people? And
Yeah, we go all over the world, and we do turnkey or what we call shell and systems. And there's a packaged plan book, but now when it's just simply out of date, because when people choose something out of the packaged plan book, we try to move them into the new global application of that, which we don't have put into a packaged plan book yet, but it's still similar. And so a lot of people get us to do what we call shell and systems, and that's the structure and the power, water, sewage systems installed. And sometimes no doors, no floors, no ceilings. We define what you want us to leave out, and it keeps the price, cuts the price by 30, 35, even 40%. These buildings are labor intensive, so we keep these pies going. Usually it's like ballpark, it's like something like 35% materials, 35% labor, and then, 70? And then you got subcontractors like your excavator, your electrician, and your plumber. They end up being in the neighborhood of 15%, and subs. And then the rest of it is systems. If you're hiring a contractor like us to do it, there's profit, and then there's systems. But the thing to consider is that labor and materials are pretty close to the same. So if you're going to build the house, and they're in the neighborhood of 35%. So if you're going to build the building yourself or seriously participate in it, there's where you can cut. You can't really cut on materials. They cost what they cost. You can't cut on systems. They cost what they cost. If you know some subcontractors, maybe you can get a break. But if you're building or contracting the building yourself, you can cut profit out and greatly reduce labor to the point where you can cut, 35% out of the building. Now then, if you do that and do shell and systems, you can, the $205 a square foot that I say these costs can probably be cut in half depending on your approach. I say $205 a square foot because some people, it just shows you what these cost if you absolutely outright buy it. I've had these seminars going on for, 15 years probably or more, and in the first book I said beavers and wasps can build their own homes and people can't, and I made a big thing of that. Well, I had my head up my ass on that one because some people should not build their own house. I had two, in one seminar I had these two couples and they looked very much the same. I couldn't even, I got them mixed up. The guy was tall and skinny. They were elderly, 50-ish maybe, or late 40s or something. My heart bleeds for them. But the guy was tall and thin. The woman was short and heavy. Two couples almost looked identical. One of them, they both got all inspired and bought land around house and started building their Earthship. And they both, I always advise people, if you're going to do it yourself, start off with just one module. This was back in the days when we did use more than these packaged and the global designs. So I talked them both into just doing one U first to see how it went. And one couple did a U, was successful, did another one, did another one, did another one. I think they even did another one. They got a giant building full of food and everything. The other couple got one U not even done and got a divorce and hated me. So these people couldn't even operate a shovel, whereas these people could, and they looked just the same. So you never can tell. But what I'm saying is, some people should do it, but when you make a blanket statement like beavers and wasps, you're just shallow thinking, I guess.
So the 205 is basically if per square foot, yeah, but I mean that's turnkey to say have you build it all the way out through finish.
Yeah, that's basically what it costs, and when we've done it all over the world, and that is a figure that is, in the U.S., you can get the same kind of home that Habitat for Humanity builds for probably $150 a square foot. You can get a junky little frame home for less. But the price of a good, brick veneered, well-insulated thermal home that's not really a carbon zero home, but just a good home, is in that ballpark all over the U.S. And like I say, in Santa Fe, they're even a lot more.
So you're not saving money on utilities and everything.
Right, and that's a point. Like say you take, say they cost the same. Say you compare it, and an Earthship costs $205 a square foot, which maybe equates to, say it costs $300,000 to get the size of a home you want, and it costs the same to get a conventional home, and then your mortgage payment on $300,000, if you're lucky, could be a couple of grand a month maybe, and it would be the same here. Then on the conventional home, you'd have to add between $500 and $1,000 a month on utilities to your living expenses, which would make them in the neighborhood of $3,000 a month. Whereas the Earthship, these buildings like the corner cottage, the only thing they use is cooking. And if I were living there, I would be cooking with a solar oven, and I'd rather even use a microwave that runs off of the solar power system than a propane oven. So, but in the worst scenario, I'm saying, the utility bill on one of these homes in this community that we're doing all over the world is $100 a year.
And that's for gas.
$100 a year for your utility bill. So that's not bad. That's not even worth putting in here. Whereas your $500 to $1,000 a month does affect your living expenses. So that's the overall living expenses of a carbon zero home can actually be less. Did somebody else have a question on?
Well, there was one question you wanted to have come back, which was the structural
Oh.
integrity of a can only or a bottle only.
Oh, and somebody had a bearing strength question too. So on the can walls, which you will probably be doing some of here in a little bit, cans, bottles, they're all laid either in cement or dirt, mud. And a can wall, for instance, is laid like this on a patty of cement, and then you put another patty of cement and the cans are there. The point here is that the cement is sort of like a matrix that the cans are in. And the truth is, the cans could just, they won't because they're aluminum, but they could erode away and just be gone. And you'd have a wall that was cement matrix with voids in it. So the point here is that the structure of a can wall is really the cement matrix. And so by virtue of that, cans are simply a method of forming cement or mud wall. So they're really, there's no structure on this aluminum flimsy little can. It's just a way of forming this matrix that is the structure. And so that's the case with bottles or cans. And we use them. See, I think Kirsten maybe showed you in the slideshow, we started off doing can buildings just as a contrived effort to recycle. That thinking is what led us to use tires, which now is beyond. I mean, I don't care if it's recycling or not on tires because they're such a bomber way to build in terms of mass, in terms of structure, indigenous to the entire planet, and so on. And which brings me to this question, the bearing strength of tires. Of course, Kirsten showed you the cement truck driving up on a loaded tire wall. That's the way I got it approved in the old days. 25, 30 years ago, I took that picture down to the state authorities. And I said, I want to build some buildings this way. And I showed them that picture. And everybody in New Mexico drives a pickup truck. And so this old guy on the staff down there got up and said, well, because they were all wondering, well, should we let this guy do this or not, or is he an idiot or whatever. So this guy got up and said, well, if you drive your pickup truck through a frame wall, you go through it and out the other side and maybe you break out your windshield. If you drive your truck through one of these walls, you will die. So they all laughed and approved it. That was the approval in those days. And so it's definitely, one thing I didn't mention in terms of it is we batter the walls. We do what's called battering the walls. These you can see the slope on this wall. If we're burying up against the building, we slope the wall each course a little bit into the burial. That's called battering. That leans the weight of the wall into the weight of the burial and kind of balances it off. Then there's a coefficient of friction from the weight of a 400-pound earth-filled tire on another one, because there's no mortar. It's just weight and mass that hold these things together. The bearing strength secret is, or truth, in a normal frame house, they make like an 18-inch, 16 or 18-inch wide footing with steel in it. And they put a 2x6 or 2x8 wall on it, and there's a force going down of the bearing of that wall with the roof. And the way the engineers calculate it is they take different soils and they figure out the bearing capacity of the soil, and then they figure out the weight coming down. And that footing, the purpose of that footing is to spread the force coming down out to being something that will cause that to float on the bearing capacity of the soil. So if it's a real cheesy soil, the footing has to be a little bigger. If it's a real hard soil, the footing can be a little smaller. The average rule of thumb situation is on a frame home, you end up with a 16 to 18 inch wide footing. Well, a tire wall is already significantly wider than that. So when the engineers do the takeoff on the tire wall, they find out that the tire wall is already wider than its required footing. So the tire wall becomes a monolith that is its own foundation. So tire walls do not need a concrete foundation. When you do the weight coming down and the bearing capacity of the soil, the tire wall is essentially floating on the on the bearing capacity of average soils.
Doesn't a conventional footing also go below the frost line?
Then you take a lot of times the conventional footing, if it's in an area where you got a frost line, they dig down, they put that 18-inch wide footing in, then they come up with 8-inch block or something, and then they go up with their frame wall. So you have to go down to below the frost line, because say in an area like this, it freezes to 3 feet down. But in a tire building, you don't have to do that, because the tires go up, the earth comes up against them, here's the roof, the 3 feet down can't get through the thermal wrap, and the bearing is occurring 8 feet down. So we, in a buried Earthship, we recreate the frost line to the point where it's not has no effect on the building.
How about the greenhouse?
Then the greenhouse out front has usually a couple of tires, and sometimes 3, and we put the leaning face on the greenhouse, and then we insulate that and out a little and bury that. And it's the insulation again that keeps us from letting the frost line get into the bearing of the tires. And at another point there, a concrete footing is brittle, is rigid, and any heaving will crack it. If you did get heaving on a tire wall, there's no way it can crack. It's resilient. It's hard, but it's resilient. So, because it's earth. Earth is more, over time, earth is more liquid than it is rigid. And so any heaving that would happen is not going to have much of an effect, if any. And we still block it with rigid insulation. Yeah.
On the vertical bearing strength, have you ever calculated pounds per square foot?
We have an engineer report that got into
I
that.
just didn't, I read that, but I couldn't see any.
Then I don't think they have come up with a max of what it would take, other than the concrete truck on the tires pretty much.
I mean, that's going to be 2,000 square foot.
Yeah.
Earth, what are the considerations about putting earth over the roof? Like
Oh,
roof?
so we've done them. The old days we would do that. It's nice. It's a soft situation. I'm into the aesthetic effect of these things being as soft as possible. Burial, roof structure, insulation, and in a case like you're talking about, you bury the roof. Now the reason we used to do that, the reason we steered away from it was, one, we started observing that a person standing in a room, the ambient temperature that they're going to feel is coming off up to their head height, and that's it, because this is all about ambient temperature, not like a forced air furnace or anything. And so having mass above your head doesn't really achieve anything. What it does do is make your structure have to be a whole lot heavier to support it. And when you have grass on your roof, you don't catch near as much water. And in an area like this, that's why we've gone to metal roofs, is because the metal roofs are so sensitive that we have seen the gutter dripping into the cistern from morning dew. And you won't see that on a grass roof because it gets absorbed. So due to water catchment, weight, expense, and lack of effect, we don't do grass roofs anymore. What you will see if you walk around, and I'll go into this more tomorrow, the roof on this building was a material called bry, and it goes on with a torch, and it catches really nasty water, so we put acrylic coatings on it to make it catch cleaner water, and they peeled off. So and then we spray foamed it, which you can't get all over the world. So this was a learning experience. The next two buildings are this EPDM. The next building is the EPDM material. It's a rubber. It catches pretty clean water, and it lasts 10 or 15 years, and it's going to need repair over there on that one pretty soon. Then the next building is when we started moving to metal roofs. But when we got into metal roofs, the detailing of a metal roof is much more involved than a rubber roof. So it caused us to have to try to get the roofs more simple. So then you'll see on these global ones, the roofs are super simple. They're just set up for sheets of metal to be laid on there and screwed down, and boom, it's done. Catches super clean water. But it did require redesigning the mechanical aspects of the building so there's not a whole bunch of penetrations. We cluster them together. So the whole design of the building is aimed at making the metal roof more simple because the metal roof is so valuable in terms of catching water. So all of these things go in together, yeah.
So with the metal roof and that's facing north now, in the winter does the snow still melt?
Well, I'll go into that more thoroughly tomorrow, but since you asked it, I'll answer that part of it. This building was old school. I mean, Kirsten probably showed you up at Reach, the steep community in the mountains. What we observed up there, they get more snow up there than down here. There'd be 2 feet of snow on the roof, and the roofs were north facing, like that. The glass on the front was south facing, and here's the building. And we get a bunch of 2 foot of snow on the roof, and we just watch it evaporate, no water. And so we had one other roof that just by chance, due to the mountain, was sloped this way. And we watched that roof on a day like today, melting and water running into the cistern. Observation was a south-facing roof is going to catch water, a north-facing roof is not. So we changed all of our designs to do this south-facing roof, kicking back up with the greenhouse, just like here, to south-facing roof. It could be very subtle, we observed, to get just a bit of sun rays on it to melt the snow, kicking back up at the winter sun angle to still get the heat, created a valley which caught water, but due to our inexperience in water catching roofs, you know, if you've got a roof like this, you can make a mistake and you may have a drip. If you've got a roof like this and you make a mistake, you got water on a coffee table in a living room in a lawsuit. So, back in court. So this is just more expensive to detail. And with metal, it's got, you know, that corrugated metal roofing that's really the most sensitive and best material. It's a lifetime material. To use for a roof with this kind of a roof design is expensive, problematic, and whatever. And we did it. We did it at Corner Cottage. We put rubber going up under the metal, and it's expensive. But it works. It works great at Corner Cottage, but we're always trying to get these things to be more affordable. So what we did was we observed, okay, when the sun's out, the snow on the roof, this is the case with every aspect of those 6 points. We've gone through trial and error, learning, and you know, there was no books about this stuff. We just had to try it and fail. Failure is a big, failure's not allowed in the real world, really. You get sued. But it's really, what we have here is a forum for failure, basically, because failure is where we've learned everything. So you have a couple feet of snow, the sun hits it, and it melts. When the sun is not out, the south-facing roof is doing no good because the snow's not melting. So what our observation is, okay, when the sun's out, we're melting snow. Well, why can't we take that just a step further? You've got a north-facing roof. The sun's out, it's not going to melt. So we put panels, water glycol panels up here that pipe water in tubes through the back of the metal roof. It melts underneath the snow and convects up the metal roof. The gutter's right here. So again, whenever the sun's out, we are running a little pump and running hot water from the panels underneath the 2 feet of snow and getting a trickle of water. It works when the sun's out. When the sun's not out, it doesn't work, but neither does this. And what we have is we did the math. This roof ends up being 10 to 15 grand cheaper than this roof with all the things considered. So we knocked, you know, it takes 2 or 3 grand to do this little system, which then also doubles as a domestic hot water. So in the rest of the year, this gives us a tank full of hot water, which I'll go into more tomorrow. So it's killing 2 birds with 1 stone. We're still melting water, and it saves us a whole lot of money on the roof. So what you'll see on the later buildings, the one that Kirsten's going to take you to called Sutton tomorrow, is you'll see the solar electric panels across the front, and then you'll see 2 big other kind of panels. They are the panels that heat the hot water to melt the snow and to give you domestic hot water. So on the front of the Sutton house, say, and I'm getting a little bit into systems, which is more tomorrow, you're going to see the photovoltaic panels, and then you're going to see these 2 square panels that collect water to heat the roof, and in between them is another little panel that runs the pump that pushes the water. So it doesn't steal power from your domestic household power system. It just, whenever the sun's out, you got water melting your roof. If you don't want it, you got hot water for your bath. And so that's just we consider all of these things, we keep learning, we keep evolving, and the building keeps getting more simple and easier to build and cheaper and so on. Did you have a question?
Yeah, when you go to design like a custom Earthship or something, what are some of the things that go through your head?
Things that go through my head. Well,
In 5 words or less.
let's see, bacon, margaritas. Well, in a way that's a good question, because first of all, I try to talk people out of doing a custom Earthship because a custom Earthship is not as good as this. It's like going to Dodge Motors and there's a Chrysler sitting on the showroom floor, and you want to customize it. If they would even do it for you, it'd cost a fortune. The thing that they build is what works. They just build more expensive ones or cheaper ones. So but I do customize the buildings to a particular climate. For instance, getting back to our same old global Earthship here that I've been drawing all morning, with the battered wall, the thermal wrap, the now north-facing roof that we've explained, the double greenhouse, and the convection engine and the tubes and all of that. Okay, if I'm going to, then I apply that to what I do. The first thing I do, when a client will tell me where they live, I'm still going to, this is what I start with. But then I get the annual rainfall. If they have a lot of rain, that means I can have smaller cisterns and probably have to have more solar panels. I also get the rainfall, and I get the winter low and the summer high. Now, here our winter low is 30 below, not sustained, but every once in a while in the night in the winter it gets down there early morning. And summer is 105 or something like that, 104. So if you've got a winter low of 40 below, and so I collect that data. You got a winter below of 40 below, but another thing I get is the number of sun days. We have here 300 on average sun days a year. Someplace in Maine may have 35 or 40 below, similar to us, but they have 200 sun days a year or 190. So that information tells me how to tweak the design. So in the serious situation, I would say probably add the third greenhouse. You'll see it at the Phoenix. There are places in the Phoenix that have the 3 glass faces. Then the thermal wrap that we put on around the building to insulate the mass, we would take it and put it under the floor, just in the living area where the people are. We don't need to put it for the plants, but you'd go down and insulate about 18 inches because you're trying to stretch all of these aspects to give you a little bit better performance to make up for the lack of sun. And so there are tricks like that. If the things that are adjustable are a few tweaks on insulation, greenhouse. If you have less sun, then your power system, which I'm going into tomorrow, gets into more panels. Like we did one in Vermont. We did insulate the floor like this. We just simply doubled the power system. We found out that they have about half the amount of sun days as us, so we doubled the power system. We actually put 2 full-on power systems in. And that's interesting because these power systems are designed for Earthships. You can't take our power system and hook it onto a regular house because a regular house has a lot more demand. The the things that we encounter, like with that have taught us to point that out to people, is we built one of the early buildings before they were called Earthships, pit houses, which worked similar, but it was just before we copywrote the name Earthship and everything. And the people moved in it, and everything was working and everything. Well, they called up one day and said, your power system is not working. And so I talked to them on the phone for a while and found out that I was quizzing them. I was trying to troubleshoot and find out why the power system wasn't working. And they said, well, we got some guests. And I said, well, guests can tax the situation. They said, well, it's not really hurting anything because they're over here in their Winnebago right next to us. But the Winnebago was plugged into the house with all of its fans and refrigerators and everything. So it took me an hour phone conversation to find out that they had plugged a Winnebago into the building. The power system is made to run the building. It's not limitless power. So lots of things like that have happened so you have to point out to people, this power system is integral to your life in your home. And, if you plug in your Winnebago, it's not going to work. Yeah.
In your opinion, I know you built these all over the world. Is there one climate that's easier to build than Earthship in, that makes it cheaper, easier, that makes it perform better?
Well,
If you had to choose one?
Obviously, I think sunny climates are easier because you can get more power, more energy. Sunny, cold climates, But we've done them so many different places that it's just, our effort is to make them a universal design that can take care of people anywhere. And we used to have, as you can see, all these different designs, which are really going to go away in our new education facility because we're going to be presenting the current situation more. But we've gone through so many different designs, and they were all evolving due to all the different climates we were encountering. And we started seeing that, well, if we can standardize a design that just gets tweaked for every climate, it becomes more available to people. Because that's the big thing, is that whatever you do, it's got to be easy for people to get it, to acquire it, to build it, to buy it, whatever. It can't, if you get too much custom and tailoring, it just makes it too expensive. It keeps you from standardizing. The industry, the automobile industry, all the different industries have done a good job of that in terms of standardizing their product, no matter how bad the product is. They've standardized it so people can get it. And so we learn from that, because part of getting something out there is making it so that people can obtain it somehow. Somebody had a question over here?
Yeah, I was wondering about glass technology. Have you looked much into sort of ergon-filled glass and all these tints for different scenarios?
Well, another thing that we're trying to do, and since we go around the world a lot, we get caught up in this. One thing that steers us away from that is we want to make these buildings made out of products that are available in even a third world country. And it turns out that tires and cans and cement and rebar, some wood, is available. Glass is, so that's kept us from the high-tech glasses. But if you got glass on a north side for whatever reason, or east or west even, then some of those kind of glasses, if you can afford them, make some sense. You don't really need to use them on the front face because they retard solar gain, some of them. And of course, the orgone filled, then they're just radically more expensive. So we're trying to use materials that are, I'd rather do a third greenhouse and justify it with more water catchment, more food production, more sewage treatment. And see, that's another thing. If you're in a climate, a serious cold climate, that your black water system, like we have here, that green up the mesa, is not going to grow for 6 months because it's severe cold. That's another justification for another greenhouse, not only is it a buffer zone, a water catchment, and a sewage treatment, it lets the plants grow year round. Maybe it'll get down to 40, but plants will live if it's not freezing. So we, rather than go into higher tech pieces of glass, we go into just more greenhouses because it's really easy to justify them. People can add them. Like if you're in northern Canada and you build the global Earthship, then we set it up so that you can add this. And we're doing that on quite a few right now. Phase 2, they're gonna be surviving reasonably well with this, but they're gonna be super comfortable with this and have more plants, more sewage treatment, and so on. Yeah?
When you add the third greenhouse, why do you pitch the roof up? Why don't you just maintain that straight line and the simplest roof design?
Because I always draw it that way because I relate it to the winter sun angle. So this angle would be less closer to the equator and steeper. No, this angle would be less the further north you go and closer to the equator you go, it'd be higher, except then when it gets warm, you don't even need it anyway. So in a northern climate, I match this line with the winter angle of the sun so that this structure, this is glass, this is insulated structure, so that the sun makes it all the way into the house still. So I don't want to block any sun by this buffer zone. I just want to trap more temperature so that this minus 40 degrees is not felt all the way in here where the people are. So I'm still trying to get the sun in.
It wouldn't be cheaper to just go straight from that highest point to the lowest point in the back and not have that
Like this.
detail? Yeah, like why not do that?
Well, if you're going to do it from the get-go, yeah, that could be structured. But a lot of times, that's one way you could do it. But since this, in our efforts to standardize, since this is worthy of standardization, this global model, then this is an add-on to the global model. So rather than change the whole structure of the global model, we can keep it standardized and add this. And when you do add this, you find that you have to adjust it. So you'd be dealing with a separate set of drawings for every latitude, and we're trying to avoid stuff like that. Yeah.
Actually, I have 3 questions. One, can you talk a little bit about what affects room depth? If you have a U, I think Kirsten was saying you have the ability to go a little bit further from the greenhouse.
Yeah, well, room depth was in the early days a discussion, because if you have a mild winter, then you can make the U's pretty deep because you're not getting that cold. And in fact, it's cooler back here in the summertime. And if you're having a severe winter, you make the rooms more shallow because then the sun and the airspace you're trying to heat is less relative to the similar glass space. In other words, this is considered your source of heat. So you got the same source of heat for a much larger space than this much smaller space. So this is what you would do in a severe winter. This is what you'd do in a mild winter. So that was the way we played with the U's. But then when we started going to just making the whole building surrounded by the 7-foot thick thermal mass, thermal wrapped wall, we came up with 2 depths. We have one of 20. That's just to the vertical face. Then the greenhouse is added to that. So we have 2 depths we use now that are kind of universal to the world, really. 20 and 17. 17 is more sensitive to performing better. 20 performs not quite as good in severe winter, but it's okay. And so the buffer zone helps make up for that. Then that gets into structure. If you go see our beams now span this way, not like they used to on the U's. So when your beams span this way, if you get more than 20, you start getting into super trusses and heavy, heavy loads. And 17 is the best because it's an easy span with either trusses or logs, which is what we use. You'll see both in the community. And so we're getting down to a lot of like when we first came up with the package design, it was this way. It was a lot cheaper. It was a lot easier. It was aimed, though, at being easier to put together. And we thought that we're going to sacrifice some performance by making this thing easier to put together. turned out that those package buildings really performed well. Then when we added, so you see the orange is the package building. We did a lot of them all over the world. And then we started going, well, we can even make them better by doubling the greenhouse. And then we doubled the greenhouse and got into this melting of water thing and shoved that into a doubled greenhouse with a sloped roof, and it turned out to be, we call it the global because it works all over the globe. And so these tuning of the U's is kind of old school at this point. It's back into custom situation. There's nothing wrong with the U's except that there are more details to build them, therefore more time consuming, therefore more expensive than these. The whole building is wrapped in the twice as thick wall. And so what I'm getting at here is that structure, thermodynamics, and price all go into equally determining the design of this building.
So a couple of other questions. When you modified the design of this global design, you've got the vegetation now in the front greenhouse, at the roof level. Are you trading off these skylights then? Are these skylights just not part of the design?
Well, they're gone. I mean, they're nice.
They are really
They're cool because you can lay there in bed and look up at the stars, and there's nothing to the light, but see, the buildings are more shallow than this. So you go in the corner cottage, or then there's a couple of globals that are built. You're going to find that they're just as light as this room. You don't really need that light. They're just as light because they're shallower, and they're actually cooler because now the air comes through the earth. See, if it's 105 degrees outside, the air coming through that window and out this skylight is not really anything but fresh air. Whereas if it's 105 degrees outside and we open up a convection-driven air current that sucks this air through 8 feet deep, 30 feet long of buried dirt, you have an air conditioner. It feels, up in Montana, it felt like the air conditioner in your car hitting you in the face. And so we have better movement of air, cooler air, and no openings in the roof. Like you go up on the roof of some of these buildings, you're seeing, some of these newer buildings, you're seeing no detail. Detail is money. Detail is time. We're after the thing, so what I'm saying is time and money do affect design because that's going to make it available to more people if it's not full of detail. Like my original, and I still look at things this way. First of all, I want it to work. Like we're working on this heat bulb thing now. I don't care what it costs, what it looks like, how much space it takes up. I want it to work. I want to be able to put one in a corner of a room in Norway and have it emanate heat. And I'll stop at nothing to get that. But then after I get it working, then I'm going to try to make it affordable to people to buy and easy for people to acquire and on and on. So the first designs that we had with the overall building were, we don't care what the building looks like. A lot of the ones Kirsten showed you looked like they landed last night. They weren't marketable, but they illustrated to us that you can do this. So I keep that thinking as I go through to get more into your question too. Whatever it takes to make it work without fuel, I will do it. Then I will try to take it into the economics and the simplicity of making it more available to people. But there's no sense in making it economical and available to people and easy to put together if it doesn't work. I've got to go through the making it work process first. And that process is at all cost. In other words, there's nothing that should stop you from trying to make a building that doesn't use fuel. Whatever it takes to do that, you have to do it. And that's kind of how these things all evolved. The buildings early on worked just like this one, but now they're more available to people, less maintenance, more user-friendly, on and on and on. Yeah?
Has anybody, probably a silly question, but has anybody tried to get any of these structures insured?
Yeah, they actually have.
Okay.
Yeah, they're both the banking, lending, and insuring are slowly getting easier and easier because actually there's a trend it got slammed because of the recent economic crunch, but there is a trend toward banks and insurance companies actually starting to favor carbon zero green buildings. They see if this building is not going to be a white elephant needing a ton of fuel in the future, then it's a better risk to loan on and to insure. So there is a trend for that. Used to be that banks wouldn't touch them, you know, they were too weird. But now that's another thing. Even though I don't necessarily agree with the economical world and the bank world and the insurance world, I hate insurance. But the thing is, we have to go there to relate to the masses of people that need these. And so it's kind of a, you know, we will not stand on ceremony about certain things, just to, in other words, to make this palatable to the large amounts of people. We can't be, what do you call it, fanatics, although I guess I am a fanatic, but yeah.
On you were talking about the depth being 17 or 20. If a person is more sensitive to heat, say 105 is really hot for some people, would you suggest that, or adding another greenhouse on front to keep the mainstay?
Well, that's a good question, because see that you're just getting into, everybody's getting into all the little tailoring tricks to tweak this. Yeah. I would, because of the economics of structure spanning 20 or 17 feet, right. I wouldn't go any deeper than 20. I would, in fact, stay 17. I would add the greenhouse, because not only is this greenhouse a buffer zone for keeping the cold from finding the internal living space, right. It also keeps the heat, and usually in the summer, the sun's higher, so this thing ends up blocking any sun from entering the first greenhouse and the living space. And when you block the sun, you're in shade. And you can still play the convection game out here. We put skylights in out here. And if this greenhouse is in shade and this one's in sun, then you close these skylights, open these, pull the air through the whole damn thing, and you still got the convection engine, still got the cool air coming through the earth, and you got no sun. So you're playing with your sun angle, and we're trying to standardize a depth for structural and economic reasons. People will say, you know, why can't you go 30 feet with this? Well, then you got to change the whole structure. You can customize till you're blue in the face, but there's no real reason to do that, because you can stay cool without going deep. Sometimes I would consider popping out a little earth room back on the back side that's really an inner sanctum, you know. Yeah, it's a custom thing, but you know, largely custom is just an additional cost. Yeah.
We have intentions of bringing this technology to East Africa, and I believe the area where we operate may be the only area in the world where tires are actually a commodity. You can't find them.
No, they are in India.
What's that?
In India, they are a commodity.
Okay, really? Okay. Well, thank you. But so, I mean, what would be the best alternate to using tires for your mass?
Earth.
Just earth?
Yeah, like look at we've been talking for several years to different factions in Africa, so we've obviously been thinking of it, and did some stuff in India and talking to more in India. And tires are, you know, they are in 90% of the planet a thing people want to get rid of, but where they aren't available or where they already use them for sandals and all kinds of other things, then you don't have to have them. We are, and usually in Africa then, you're looking at not sub-zero freezing temperatures, you're looking at milder temperatures. What we have been leaning toward for some of our builds in Africa that may or may not happen, well, we're doing one in Swaziland, but that's going to be up in the mountains, so it's going to be tires. But the wall around the building next door and the wall surrounding the tower out here is just glass bottles, could be plastic bottles, laid in mud, sand, and straw. And so again, it goes back to that original conversation when I just started the second half here about the structure. These bottles and cans are simply a method of forming a cement or a mud wall. Take a look at the wall surrounding this building next door. It's a pretty strong wall. Yes, it is on one course of tires to get it up off the rain, but that could even be dealt with. So mud, we're talking about using mud and glass or plastic bottles. Now, it's my understanding that in Africa and my observation in India, that plastic bottles are available by the billions because a lot of people drink bottled water in all, so you should be able to find bottles, if not bottles and cans, not necessarily even aluminum cans. But these beverage containers that do occur all over the globe can be used to form mud. And you can do what we did out here. You can't see it because it's covered now, is we did the mud and bottle wall, and we actually had a tire wall, and we filled the inner with pumice. And of course, if pumice is not available, straw, grass, whatever. So you can make the mud walls as a sandwich of insulation in between, and the insulation can be whatever you find. In Bolivia, we went out and got paja, from the fields. So the mass is the storage of temperature in a climate like a lot of Africa is not going to be as serious because you're just looking for shelter and shade. And so then the thermal mass storage of temperature is not as important an issue, and you can still use the earth to build with. Yeah.
Do you have the opportunity to work with any sites where microhydro is available?
In Scotland, we had that, and the power system that I'm getting into tomorrow that we use, that we pretty much have invented, does take power from wind, sun, microhydro, and just a subtle little stream or even a small river. If you've got it on your land, yeah, you can put that into the kitty. Because a lot of places don't have as much sun as us, so we have to combine wind and sun. And if you got
water, no
yeah, if you got water, no sun, then the system will take it from wind, hydro, sun, line grid, or a generator. In other words, it will take all of that and put it into your batteries, no matter what you can get your hands on. Was there a question over here? Yeah.
The greenhouse, the third one, how big can that be made?
Well, it's pretty. You can get pretty big with it. We like to take them big enough if you're going to go for that to get trees, citrus. The Phoenix has got citrus trees in it. So it's a question of, if you get way out here, here's the answer. 10 feet is a good starting point. Then you get 11, 12, 13, 14, 15. The further you get out there, the higher it has to get, because here's your angle. You have to stay keeping the winter sun admitting. And so then the volume of it gets so big that if you got out there far enough, it would freeze. It would get, it's going to, the performance of it, I like for ours at the Phoenix, which you'll see tomorrow, I don't like for it to get below 50, let's say. Reason being is because I got tilapia in there, and the lethal temperature for tilapia in the water is 60. And we lost a batch due to that. So now we've tightened the whole thing up and put a solar heater on the tilapia pond, and so far so good. We're eating tilapia. But so anyway, the point is 10 feet is a good beginning, 11, 12 maybe okay. Then when you get out there bigger, you're just reducing its performance and extending its cost.
What about adding a fourth greenhouse?
Well, I haven't come up against a situation that would require that, but somewhere in Canada, I can imagine. You Canada?
No, but we eat only raw foods, and so we would like to grow trees for all year round, fruit.
Yeah.
Trees for all year. Would that be possible?
Yes. Yeah, I would say still you could do it in a third. Because you look at the Phoenix. You haven't been to the Phoenix yet? Okay, this should answer some of that. There's nothing wrong with doing a fourth, but I think in terms of, I think 3 can give you, if your house ends up being 80, 60, 80 feet long, and you got a greenhouse. Usually they have, you got food in here, and you got food in here, and some of them even have food in here. You got 3 areas to grow food, and that's another cool thing about the Phoenix is there are so many different areas. You got all these little microclimates where salad grows best here, bananas grow best there, As a matter of fact, there should have been last night or today or something, banana bread from the Phoenix. Just harvest a big fat bunch of bananas. And we always have bananas. People, year round, we have bananas in all these buildings. Yeah. Yeah, all year. One of the houses has got bananas year round. And you can, some people say you can survive on bananas. And yeah. So you can have, you could have bananas year round. I mean, the Phoenix is just scratching this. It's huge, and it's been going on for 3 or 4 years, but it's just beginning to scratch the surface of what we can produce. We're starting to go into layers, and I'm going to get into that tomorrow on the botanical cells with the growing. But in citrus trees, we've got, once you get citrus happening, we got one of them that has lemons the size of grapefruits, and it's amazing how much food you can produce in your own home while treating sewage at the same time. Was there another question? Yeah.
You mentioned it briefly. You'll probably talk about it more tomorrow. Have you ever used hydroponics as a system to grow food and use the gray water?
Well, our botanical cells, which I'll go into tomorrow, are sort of a cross between wetlands and hydroponics. So we have approached playing with hydroponics, but we're trying to go with, stay with simple aspects that people are used to dealing with, which is planting plants in dirt. But they still have unlimited access to water. You can, it's in a way it is very much like hydroponics.
Yeah.
Here we're just structuring the plants with dirt rather than hanging them with some kind of structure.
Sure. Plus you have a lot of chemicals.
Yeah.
From the hydroponics.
Yeah, we're not into playing with that much. We want it to all be more of a natural process that we can.
So you don't feed the plants in here at all? It's all just from...
No, when you see the Phoenix, all the Phoenix is the sewage system. And the nutrients from that, I'll go into how that works tomorrow, but that's actually what the thing looks like. The roots go down, they have access to water constantly. What I've observed is that when you water plants with clear water, they grow. When you water them with gray water, they explode. They just go crazy. And so I've seen plants do things that I never had seen them do before with gray water. So it's like they're happy. And they're stronger and more resistant to bugs and stuff like that. So there's a whole lot to go into on that conversation. All right. Then we'll do the same thing tomorrow, only we get into the systems really heavily. Power. We start with water and sewage because they're interrelated. And then power. And then you break tomorrow and go on a tour of all of these houses I'm talking about and see everything I'm talking about if you're not staying there already seeing it. All right, we're going to work now in about 45 minutes.